Now we're going to do some pedigree practice problems. Just to go back and review those a little bit. And here's our part 1. Affected male would be a colored in square. Unaffected male is a square. Male deceased, that's the new one we haven't seen. If it's a line through, just know that means that they're deceased. Again, females are circles. If they're shaded in, it means they're affected by the trait that we're looking at. And there's another new one. If it has a P in it, there's a pregnancy there. Mated across, that means that they are mated or married if we're talking about people. They're connected with that horizontal line. Number 1 says do a Punnett Square for a cross shown below between a male and a female, both with hemophilia in the X-linked recessive disease. Okay, this is a sex-linked on the X chromosome. Females are represented by a circle, males by the square. The darkened shape means the individual has the disease. And it is X-linked recessive hemophilia. So that Punnett Square, we'll do a Punnett Square. So this is what that Punnett Square would look like. If the female is affected, she would have to have 2 X chromosomes with that recessive trait because it said it was X-linked recessive. It said both parents are affected. Here they're both shaded in. So she would have to be X little n, X little n. And then he would only have 1 X chromosome, so his X would be X little n. But then he has the Y chromosomes and nothing to counteract that X. So their children would end up X little n, X little n, X little n, X little n. These would be 2 female offsprings. Both would be affected. They would both have 2 of those recessive alleles to show that recessive trait. These 2 would end up being male offspring, but they would both have the X with the little n, so they would be affected as well. Let's see, it didn't ask anything about the percentages or anything, but it would be 50% affected daughters. All the daughters would be affected, but we expect roughly half daughters, half sons, but all the offspring would be affected with the anemia, hemophilia. Again, a thing to remember about the X-linked disorders, X-linked recessive disorders, they're not often seen in females because they do have to have 2 X's with those recessive traits on there for it to show up. More often than not, they'll have an X little letter and then X big letter. So that big letter, the X with the normal allele, would cover up the other X, the recessive allele on the other X. So we don't see it in females as much. Females are often carriers. They'll have that X with the dominant allele and X with the recessive allele. So they do not show the trait. But then if they have a male child, then that male child would have that trait, because in the male condition, if that recessive trait, they only have to have that 1 recessive allele because they do not have another X to counteract that. They're XY, so there will not be another allele here to counteract that recessive allele. So anytime the recessive allele shows up, even if it's just 1 in the male, then the male would express that trait. Females more often than not will have an X little n or X big N and be in the heterozygous condition, and they will be carriers but not show the trait. In this case, X little n, X little n. This is an affected female because she does have 2 of those recessive alleles, but more often than not, that's not going to happen with the females. Like color blindness, you'll see it more often in males because, again, it's an X-linked and there's not another X to counteract that. But more often than not, the female will have a dominant and a recessive. She'll be heterozygous and be a carrier but not show the trait. Number 2 says write the genotypes for the parents represented here next to their shapes. Then do the Punnett Square for the autosomal recessive disease. That means autosomal recessive means it's in one of the other chromosomes, not the sex chromosomes. Somewhere in between 1 and 22 on those autosomes. So it's an autosomal recessive this time in the cross between the male and the female. Okay, so if it's recessive, she would have to be little letter, little letter. And this could be a test cross. We don't know for sure. Let's see. Did it tell us? Parents of the shape, do the Punnett Square. Autosomal recessive between this male and this female. Okay, so she is little letter to little letter. We don't know for sure. He has at least one big letter. Again, this one would represent a test cross. There are two possibilities for this unaffected male here. The female is affected, and it's an autosomal recessive, so we know she has to be little a, little a. So she's little a, little a. He has to have at least one big A, but that's all we know is that he has one big A. He could be big A, in which case we would end up with 100% offspring being heterozygous big A, little a, with the phenotype of being unaffected. He could also be heterozygous and still be an unaffected male. He could be big A, little a, in which case we would end up with big A, little a here, big A, little a here, and those two would be heterozygous. 2 out of 4 would be heterozygous, phenotypically normal. But down here we get little a, little a, and little a, little a. And these two would be 2 out of 4 homozygous, recessive, and phenotypically would show that trait. There are two possibilities for that cross, depending on if he's homozygous or heterozygous. Again, that would represent a test cross. We have a homozygous recessive parent crossed with an unknown. Number 3 says the father shown below has hemophilia and X-linked recessive disorder. So the father's going to have only one X, and he would have that recessive trait on that X, but because there's not another X to counteract it, he shows the trait. Okay. So he has an X-linked recessive disorder. If this couple had a son, could the son have the disease? What genotypes would be possible for the son? Well, the mother is unaffected. But, again, it's X-linked recessive, so she could be X dominant, X recessive. She could be heterozygous and be a carrier. In which case, if she's a carrier, then she would pass on that X. Let's see. She could pass on if she is. I can get my thing to go where I need it to be. She could pass on that trait. She could be H. Oops. She could be X. Big H. X. We can't know for sure the genotype of mom here because it is a recessive trait. She's not showing. She could be heterozygous. She could be X big H X little h. Or she could be homozygous dominant X big H X big H. Okay. Dad here only has the one X, and he is showing that trait. So he has that trait on his X. So he is X little h. And even though it's recessive and he just has one, it still shows up because he doesn't have another X here to counteract that one. He has a Y, and there's not an allele on that Y to counteract that one. So the son's X has to come from mom. So if mom is heterozygous, she could give a big H, and then dad give his Y. Or she could give a little h, and dad give his Y. And so if mom is heterozygous, there's a 50-50 chance that that son will be affected because mom is a carrier. She could pass that trait on to her son. In the case of her being heterozygous, she would pass on that little h. In this case, he would be affected. If she is homozygous, he would have to be a normal son. If she's heterozygous, there's a 50-50 chance that he could have the hemophilia. Okay, number 4 says the couple shown in the pedigree below have 2 children. One's a girl with the disease and one's a boy without. Shaded in means that she has that disease. And we need to figure out the mode of inheritance. Is this disease autosomal recessive, autosomal dominant, or X-linked recessive? And I'm going to explain how we think so, and we're going to fill in the genotypes. And so this daughter's affected. None of the other 3 are affected. So, if it were a case of it being dominant, then they would have to these parents would have to have it to pass on to this daughter. They do not have the trait, so it would have to be recessive. Would have to be recessive, and if it's recessive, then if it were X-linked recessive, then she would have had to have gotten an X with the trait from mom and an X with the trait from dad. And dad only has the one X. So if he had an X with the trait, then he would be showing it too. So we now know that it has to be autosomal, not X-linked. It has to be on the autosomes. It has to be an autosomal recessive trait for it to inherit in this pattern. She would have to have two of the little letters, and we're going to use, it doesn't tell us what the disease is, so I'm just going to use D for disease. She has the disease, so she has to be little d. She would have to be little d, little d. Let's see if I can put it there. She would be little d, little d. Okay. So she's little d, little d. She had to get a little d from mom, and she had to get a little d from dad. But neither one of them are showing the trait, so we know they have to have a big D. And now we know that they have a little d also because they passed it on to that daughter. So mom would have to be big D, little d, and dad would also have to be big D, little d. Okay. We know that the son here is showing the dominant trait of being normal, so he has a big D. And that big D could have come from mom, and then dad could have given a big D, or dad could have given a little d, or the way around. Dad could have given the big D, and then mom could have given either one. So we don't know for sure if he is homozygous or heterozygous. I'm just going to put a D question mark there. But we do know that mom and dad are both heterozygous, big D, little d, and the affected daughter would be little d, little d. And we also know that it is autosomal recessive, so we'll go ahead and put that in there as well. That's that one. Okay, number 5 says, for the pedigree shown to the right, is it possible for the trait to be autosomal recessive, and explain why? So I went ahead and highlighted that in red so I can use red to show this one. In the case of autosomal recessive, this mom was not showing the trait, so she would be, we're just going to use D's again for disease, so she could be big D, little d. And then dad, who has the trait, could be little d, little d. If that's the case, mom could have given the daughter here her big D, her little d, and the dad could have given one of his little d's, in which case she would end up being little d, and would have the trait. Okay? And so that would work out for her to have it. And then the son here, dad only had little d's to give, but if mom was heterozygous, she would have a big D to give. So she could have given the son her big D, and dad given the little d, and then the son would be unaffected heterozygous. So yes, autosomal recessive is a possibility. And we'll put, yes, if mom is recessive, if mom is heterozygous. She could give the daughter little d and the son big D. It says, is it possible for the trait to be autosomal dominant? Yes, for autosomal dominant, it would just kind of be the opposite of the recessive situation. If it's autosomal dominant, mom's not affected, she would be little d. And then dad would be the one that would be heterozygous this time because he would have that dominant trait. So he could give the big D to the daughter, making her have it, and then the little d to the son, with mom's little d, making him a homozygous recessive, and he would not have that trait. And for the X-linked,